Today, I'm going to talk about our tool to extract data from text. So I'm going to start by stating the problem that we are going to solve. Then I'm going to present our approach. And then I'm going to dive into the details of our approach, namely tagging, querying, and projection. And then David is going to give a demo with a Jupyter notebook, and he will wrap up the presentation with conclusions. So what is the problem that we are trying to solve here? So we have text, and then we are trying to extract some data from that text. And then, for example, in what you see in the screen here, say we have a text representing with the statement of a financial institution, and then our tool allows us to retrieve specific data from that text and then produce, say, a JSON document. So what is our approach? What we are going to do is we start with text, but the first thing that we are going to do is we are going to annotate that text with tags. So for example, we can tag every single line in the text with the tag line. And then we can also say tag all the integers that appear in the text. And then in addition to that, we can also tag a specific string. So we want the occurrence of a specific string, for example, electricity delivery and rate change this billing period. Then once we have the tags, then we can use these tags to query the document and get the result. So let's look at an example. Suppose that we want this box here, the result, the text in this green box here. So what we need is select the text between the line that starts with electricity delivery, that means this line that starts with the blue, and the string rate change this billing period. So it's going to extract this text here. So as I presented in our approach, the first step is to tag. How do we tag the data there? So we basically tags associate is a tag with some locations in the document. So for example, the tag integer, we can associate the tag integer with all the strings in the text that match a regular expression, like this regular expression 0, 9 plus, or we can tag all the integers like that way. Now, another possibility is sometimes you don't want to have to tag every single thing. So for example, if you have a string like electricity delivery, you don't want to create a tag for electricity delivery. So you can just anonymously say, okay, give me all the occurrences of this string. So that's another possibility. So now, how do we represent a location? A location is defined as a triple that has an offset, a start, and the end. Typically, the offset is from the beginning of the text. But as later on we can see, I'm going to present an application where we will be nice to have another type of offset. But so if the offset is 0, that means that the start and the end is with reference to the beginning of the text. So once we have the tags, so we start doing the query. So the querying is going to do in 3 steps. So it's going to be a pipeline. So the first one, we are going to select a set of locations. And then once we have those set of location tuples, we set of tuples. So we set of location tuples. And then once we have the set of location tuples, we can apply a function to each tuple of the step 1. And then we can apply a function to the results of the step 2. So I am going to illustrate that with an example. Okay, so the first step, select the tuples of location. So for that, we can use the tuple relational calculus. So here, what we are going to select is a tuple of n locations such that each location belongs to a tag. So for instance, location 1 is in tag 1, location n is in tag n. In addition to that, we have a predicate that is going to constrain further what locations we are going to be considering. So what is that predicate? The predicate is going to be conjunctions and disjunctions of relations on locations. So what kind of relations on locations are we talking about? We have built-in and user-defined. So for the built-in, let's consider the Allen's relations for intervals. So one possibility here, we have location X and location Y. So the before is going to be true if location X is before location Y. The mids if location X is occurs before location Y, but they are adjacent, and so forth. In addition to that, the user can define their own relations to include in the query. Okay, so now, so let's look at an example. So the example that we have here. So let's try to do the step one for the example before. So the step one, first of all, we need to figure out what locations we are interested. So here we don't care about internet. So we are interested in lines, in electricity delivery, and in rate change this billing period. So the location 1 is going to be in line, location 2, electricity delivery, and location 3 is rate change this billing period. And then we need to constrain those locations further. So for example, we want the electricity, no, we don't want all the lines. Only we want the line that starts with the blue here. So we want the line that starts with electricity delivery. So that's what starts location 2, location 1 will tell me. And the other is, we want this line, we want the red part here, the rate change this billing period, to happen after this line. So the line should appear before the rate change this billing period. And that's what this predicate is going to tell you. So what will be the result here will be the result of a tuple of relations. Now, we don't care about, for the result, we don't care about the electricity delivery. We care about the line where the electricity delivery is. So the result is going to be pairs of the line where electricity delivery is and the location of the red. So, but that is going to tell me 2 locations, but I'm interested is the location of the text in between. So for that, I go to the next step, and that's when I apply here to the result, the location 1 and location 3, I apply the function in between, and there are multiple functions. So one is in between that, given 2 intervals here, 2 locations, is going to give me the location in between. And there are others like open right span, close span, open left span, and others. But then we might need a step 3. So for this, I'm going to modify the example a little bit to illustrate this one. So suppose that we have 2 occurrences of rate change this billing period. So we have one here and one here. So when we are asking for the text between electricity delivery and the rate change, so we are going to have one possibility here in yellow, and the other possibility is from here, the yellow, and the green one also, because it will be from here to here. So in this case, how do I pick up only the one that is closer? So only the green one. So for that, I apply the function shortest. So the function shortest will allow me to select of all the possible outputs here. The in-between is going to give me all the possible locations. I'm going to select the shortest. But how do I select the shortest? Eliminating all the locations that are supersets of the others. Okay, so now early on, we talk about a location that has an offset. So if we consider this table, if we consider the offset from the beginning of the text, so of course, city, Boston, Los Angeles, and San Diego, they are not going, yes.
Excuse me, we're running out of time.
Oh,
yeah.
Thank you. So these 3, they are going to, all of these, they are not going to intersect because all of them are defined with respect to the offset of the beginning of the text. But what if my offset is defined from the beginning of the line where the word happens? So in that case, city, Boston, and Los Angeles and San Diego, they will overlap. And then this specific operation of just changing the offset to say to the beginning of the line would allow me to identify columns and tables. Okay, so now I think I will pass this to my colleague, David Barrett, so he can show us a demo about how to use this tool in Python. Thank you.
Thank you very much. And now we're going to introduce Mr. Davis. Hello.
Hi. Can you hear me all right?
Yes. So Mr. David Barrett, he earned after earning his PhD, he has been teaching and applying results from computer science research to engineer solutions for large-scale software problems for the last 20 years. His expertise includes machine learning, software systems, networks, databases, programming languages, and compiler construction. And the stage is yours. Thank you.
Thank you so much. So now at this point, I'll be introducing a Python notebook we have on our release for systems. We've pasted our code. We have our code available in GitHub and the URL shown above. And we also, to run our code, you just go ahead and to use our code, you just do a pip install Conte to go ahead and be able to use the code in our packages. And this Jupyter notebook is actually part of the GitHub distribution, and it's available on GitHub and if you download the code. So the first thing I'll show is that we have two different examples we're going to be running to illustrate the capabilities of our tool and how to use it. The first example is to extract emails from headers that are contained in the body of emails, which turns out to be a kind of complicated problem because headers can appear in so many different ways. So in this case, we're going to try to extract emails, dates, and times from the headers of this body as the text shown in green. So the first thing we're going to do is we're going to import our package of the items we need, and we have several different modules in our code. The modules are available to different functionalities as you may require. This Jupyter notebook also uses some code for regular expressions for dates, times, and emails from a local module that we'll just go ahead and import, and then we can go ahead and proceed to use those imports as appropriate. So the first thing we're going to do is read the text from read the text from the file that we got from the email, and then we're going to go ahead and construct a tagger object, which allows us to go ahead and invoke subsequent methods to be able to place tags on the text that we just read. And that's in tagged email. The next thing we're going to be able to do is do the tags, as Martha indicated. And the first thing we're going to do is we're going to create tags for dates, times, emails, and then a more obscure thing called a sent date time. And then we're going to use the tag RE method to be able to do that. Tag RE takes a tag name on the left, in this case, for example, date, and then a regular expression on the right, which is a symbol that's defined in our local module that just defines a regular expression for what dates look like, and that's the second parameter to tag RE. Same thing for dates, times, and emails. And then the last thing is we have a special regular expression which we define explicitly here for sent or date, because the headers, if you'll notice, the second line of the header, the third line of the header on the top header could be a sent, and the second line in the bottom header could be date, and we'd like to just be able to grab the time from that without worrying about where it appears in the header. So we have a tagged RE for a sent date time to do that. So now we've got 4 tags, which we're then going to use in a predicate. So the predicate appears at the bottom, which is the language that Martha mentioned earlier. And then we're going to have the predicate's actually going to reference some of the tags that we defined above. And so the first part is defined that the tag is going to be referenced by. There's a 9 tuple that appears at the top. We've assigned it to tags, and the tags consist of a sequence of these tags. We have a literal from, email, a greater than symbol, sent date time, and email. And so if you go back to the headers, you'll see that those tags actually follow the convention of the orders of the top, the from, on, sent, to subject lines that we see here. Okay, so the key here is that the predicate is going to reference the tags in the same order by the index numbers as they appeared in the tags list that was passed as the first parameter to the query function that's coming up in a second. And so seek before meets is basically requiring that the tags appear in order. They could be possibly adjacent. And then we are going to make some constraints on the text so that we don't grab extra stuff. So for example, disk 0,8 less than 350 prevents one header from matching the content from another. And then the subsequent disks are requiring the from and the 2 lines email addresses to respectively select the correct ones. So once we have the tags and the predicate, and then we have the tagged email object we got earlier containing our tagged email, we go ahead and then call the query function and execute it. And what the last parameter we pass to query specifies the output of the query that we're expecting. In this case, a 4 tuple consisting of the tags at positions 1, 4, 5, and 7 in the tags list. And then those correspond to the from email, date, time, and to emails. And so then we have a method called display tuples in the tag message, which displays the results from our query. And in this case, you'll see that there's actually three lines that come back from the query. And we're only really expecting 2. And the reason we got an extra one is because we have a duplicate row that happens with the to and mail to appear. Let's see, here's the mail to, and here's the to. And that's why we're getting an extra one for this last one. So we seek to be able to eliminate that. And so we're going to make, to illustrate that we can make we're going to illustrate user-defined predicates, which allow us to define our own predicate, which we can then call on our query to be able to get rid of that extra tuple. So the way we do that is we have a user-defined predicate called not preceded by mail. It's going to take a single tag as its parameter, and that's going to become the locus method of this Malleable expression that we pass to query UDP to define our user-defined function. And the way that's going to work is it's going to look at the text of the document. It's going to look at the location that it received as its parameter. It's going to take the start of that text. It's going to back up 4 characters, and it's going to check to see if the word mail appears before 2. And if it does, it's going to return false. That's what the not symbol indicates here. So now we've added this term into our query, and then we can go ahead and execute the query, and sure enough, our extra tuple is removed. The second example is we want to illustrate how you can extract the table from electric bills. We commonly want to be able to grab tables from PDF documents, and so this is going to illustrate how we can actually grab just the text from this table in a dictionary that we're ultimately going to get, and we're going to try to read just this text and discard all the rest. The red material we're going to discard later, and then the blue is the strings that we're going to be able to reference in our query to be able to try to do the operation we need to do. So the first step, as before, we're going to just read the text from our bill. In this case, we use PDF to text with the layout option to be able to go ahead and preserve the layout, produce a text document corresponding to the PDF, which we then read into our code. And then this is what we see, and we can actually see, let's see here a minute. This should correspond quite closely to our PDF that we see here. The text of the mail corresponds quite well. I'm going to leave this here a second. So the first task we want to do is we want to get rid of the column that has all this stuff on the far right, which we're basically going to just get rid of it as noise. And the way we're going to do it is we're going to look for a column that contains the string, the total electric charges shown in the electric. And so we're going to try to find that string, find the column that contains that string, and we're going to tag all the text that appears within that column of that table as noise with a noise tag. And then we're going to delete it by replacing all the text with the noise tag, and then we're going to have the result from that. So we create our tagger object as before. We look for the electric column, we tag it as noise with tag list here, and then we replace the noise with the empty string, and then sure enough, as you look here, you'll see that the right-hand side has had that column removed. Okay, so next step is to go ahead and just focus in on the green text that we're interested in for our table. We're going to do that by grabbing some extra functionality we need to do, and we're going to look for the strings current and electric charges, similar to the way Martha illustrated in her example, and we're going to try to find the text that's between and including current but before electric charges. So the first thing we're going to do is we have a line regular expression, a line regular expression that will allow us to tag lines with tag RE, so we'll be able to get individual lines. We're going to get the location of the line that contains current that happens before electric charges, and then we're going to select the text from current up to but not including electric charges, and then we're going to choose the shortest segment of text that does that to avoid grabbing multiple pages if we have it. So the way we do that is we create the tagger as before, we tag the lines. We're going to use the query. We have 3 tags in this case, and we're going to query on those 3 tags, and we're going to grab them, execute the query, and we get back the text that corresponds to just the green part of the table. The last step is to go ahead and grab the text and be able to convert it into a form that's easiest for the computer to consume. And so we have a nice function that be able to do this called getTable. And we're going to tell getTable that the top two rows of our text are the header. It's very clever. It uses the header and the location of the header columns to be able to find the individual cells below that table, and goes ahead and creates a list of dictionaries where the keys of the dictionary are the headers, and the values of each item in the dictionary corresponds to the values appearing at that row of the table. So in conclusion, what we've done is we provided a tool for data extraction from text. We've allowed that data extraction to happen in a declarative manner, so we're not just having to do a sequence of code in Python where we're having to understand the sequencing. We just say exactly what we want with tags and queries, and we use this to provide functionality for the most commonly used data abstraction tags. What does this allow us to do? It allows us to specify the new functionality at a high level of abstraction, and this really helps when upstream text format changes. It's a real pain to change code. This way, we just change our query very simply to be able to reflect the new formatted text. And lastly, this facilitates maintenance and data extraction code. The code is short, easy to understand, write, and change. Questions?
Thank you very much. We are taking questions now. Are your slides going to be available to view later?
The slides are available on the GitHub, in the GitHub repo, so you could download those and then look at them there. And I put the I think let me give you the URL for GitHub here. And I think you can just go to this URL on GitHub, and it'll be able to have a slides underneath the next to the README file on GitHub. I think it's all.
Oh, sorry. Can we add that link to the Discord, please?
Sure. Let me find. I don't have Discord at the moment, unfortunately. Let me see if I can put it in the chat.
We can add it. Yeah.
Yeah, that's fine. Let's see here. Let me see if I could actually go there. Illustrate. This is the slide deck here, actually.
Yes, I got it. Okay, now it's on the comment section. Oh. Okay, any other questions? Okay, can't see questions. We can sort of wrap up here. So, thank you very much, David and Martha, and the link is now posted, and we are going to stop here, and there's going to be the keynote next. See you later.
Okay,
Thank you
thank
so
you.
much.
Thank you very much.